Hey guys, welcome to the second episode of my engine rebuild. In this episode I will clean my engine block, pistons, heads and perform required measurements to assess the wear of all of the engine components at 230,000 kilometers and decisions to be made as well. Let's get into it. Firstly, I need to finish off the block stripping by removing all of the plugs, dowels and back cover. Time to use my winch to remove the engine from the engine stand. Remove the cover. Remove the valve. I'm going to replace all of the engine and head valves. To remove the plugs, I will heat them up to minimize the efforts. Time for removing the dowel guides. Here goes the paper gasket. The black is going for professional cleaning. Meanwhile, I will strip off the rear covers and send them to the aqua blasting. Probably I needed a crowbar here. Anyways, another method worked. The black job is done for now. Time for the engine heads. Firstly, extract with a magnet all of the bucket tappets and mark them. They will have to go back in the same wells later on. Remove bolts, washers and the rest of the stuff. The bolts are going to be replaced by new ones as per manual. They are stretch type and one-time use only. I will do a quick valve leak test using water and air. Looks good, no bubbles. I will extract one valve to check the condition of the valve guides and valve seal. I don't have a special valve compression tool yet, so I will use a hollow socket and a magnet for this job. Using special plier, I will extract the seal. Seal looks worn. Here is the comparison with new one. Seals are made by Corteco. Now let's check the wear of the guides. As per manual, you have to align the top of the valve with the top of the guide. In this position you have to check the play of the valve. It should be below 0.5 mm. In my case it is already a bit more than that, meaning that I need to replace the guides. I've measured the valve and it is within spec. I've ordered new valve guides of a good brand. Let's check the valve play now. It is around 0.22 mm. Let's clean the deck surface and check the head warpage. According to the manual, it should be within 0.05 mm. I'm gonna try the cleaning with a plastic brush called 3M Roll-Lock Bristle Disc. This method is new to me. There are 3 colors available and the white one I have is the gentlest and it is suitable for aluminum surfaces. You need high RPMs here and constant hand motion. Let's try it out and see what happens. Looks really nice. Now let's check the deck warpage using a filler gauge and a straight edge. As I've said, the max allowance is 0.05 mm. Looks good. Now let's do the same test. Only this time I will use aluminum foil, which is normally around 0.01 mm to 0.02 mm. Looks nice. I was planning to remove the head plugs as well, but unfortunately failed, so decided to skip this operation, not to damage them completely. I've measured the camshaft lobes as well. They are more or less same dimensions. Now let's measure the crankshaft. Firstly, a homemade stand will be assembled for that. I will measure the main bearing journals. They are within a spec. And now the rod bearing journals. Same here, all good. As you remember, I've checked the crankshaft axle play before, and it was within the spec. Now let's check the maximum runout on the central journal. Max allowance is 0.15 mm. In my case, it is 0.01 mm. Time to prepare the pistons for measurement. Firstly, we need to remove the rods and rings. I will clean the pistons using my ultrasonic buff. It is good to scrape the piston grooves beforehand, otherwise they will be still slightly contaminated after the wash, like in this example. So, I will clean pistons in two steps. Firstly, using the ultrasonic machine in a 90-degree environment. Chemicals used here are kerosene, petrol, a bit of engine degreaser, and dish liquid. Time is 30 or sometimes even 60 minutes. The second step is an oven cleaner to finish off the residue. And then a good rinse. The results were really good. Meanwhile, the block was washed. I've cleaned the rest minor surfaces using roller disc. The deck surfaces were cleaned as well using Rollock. Results are good. There are some imperfections around the coolant passages on cylinders 1 and 5. But looks like this happens because of the design of the head gasket. Okay, time to give the block a good home cleaning using pressure washer and a degreaser. Rollock disc produced quite a good amount of dirty dust. The block is clean and ready for measurements. Let's measure the piston diameter first. It is measured in a specific spot, in my case 21.5 mm. Different spots are used in different engines. You need to check the manual. I will use my micrometer for this job. The accuracy is 0.01 mm. Firstly, we need to check whether the tool is accurate by using the 75 mm calibrated piece which came with the tool. Reading shows exactly 75 mm, so means the tool is still precise and doesn't require calibration. The diameter is around 92.985 mm. The piston top says 92.99 mm, so looks like pistons are slightly worn by 0.005 mm. Okay, let's put the block back on the stand and continue with the other measurements. Firstly, let's check the warpage using a 0.05 mm feeler gauge. There is no official warpage data in the manual, but according to the internet engine builders, the normal warpage is within 0.05 mm, or in some cases even twice bigger than that. Looks good. Now let's use the aluminum foil. All look good except several points in between the cylinders. I will consider this is within adequate limits and I will skip the block or head machining. I do risks here, but let's see what happens. I don't want to grind off the engine block or the heads. Theoretically, the roller cleaning should be enough. Time to measure the cylinders. We need a bore gauge for this job. This is a precision tool. In my case, the accuracy is 1 micron, which is 0.001 millimeters. Fantastic. My cylinders are around 93 millimeters, so I will have to use the required combination of pin and spacer. This tool doesn't do the diameter reading. It shows the difference between the reading you selected as 0 and the measured readings. Give it a slight attention. Okay, let's begin. Firstly, we're gonna check the total wear between piston and cylinder. To get this figure, you need to subtract piston's diameter from the cylinder's widest reading. My piston's diameter was 92.985 millimeters, so I'm going to set this figure on my micrometer and then zero the bore gauge as a 92.985 millimeters. You have to wiggle the bore gauge until the arrow finds a stable position, and then rotate the gauge so that the zero would match your found position. As per manual, the total wear can be 0.10 millimeters. Some BMW models have this figure at 0.15 millimeters. Let's check mine. Same wiggle technique is used here. As you can see, this is each cylinder's non-thrust side, the side where the piston doesn't do much wear. All of the readings were around 0.03 millimeters, which is way below 0.10 millimeters. Now let's see the thrust side, the side where pistons do most of the wear. First cylinder is at 0.075 millimeters. Second is at 0.08 millimeters. Same reading for the third one. The fourth one has the same reading as the first one. So theoretically the cylinders are still within a spec and the car can make extra 150,000 kilometers until the critical point will be reached as per manual. Now let's perform the other readings like out of round and conicity, so-called taper. Ideally you need a torque plate as well, as per engine builders, but I don't have this tool, so I will skip this one. I'm going to zero the bore gauge now to 93 millimeters. Now let's measure the most bottom part of the cylinder, where there is almost no wear, to see the factory's bore diameter. The machining factory diameter of all of the cylinders was from 93.025 mm to 93.030 mm. The manual says it should be 93.014 mm, so either my gauge is not that precise or the factory machining was not precise as well. Now let's measure the conicity and out of round. Each cylinder needs to be measured at 6 spots, something like this. 2 at the top, Two readings at each level should be done, at the thrust and non-thrust sides. Two in the middle. All of those spots should be within the travel area of the piston rings. And two at the bottom. Then I made a sketch with all of the readings. Let's see the results. Let's say here is the front of the engine, and I was measuring cylinder number 1. The bore is already having a cone shape, not a cylinder, as well as the cone is slightly squeezed, since it has out of round condition as well. This kind of wear is happening because of the travel trajectory of the piston at the thrust side, which is perpendicular to the crankshaft. Look how the measurement is decreasing from top to bottom on the thrust side, and almost no wear on the non-thrust side. The max wear is at the top, so we will use the top figures for the calculation of the out of round. We have to subtract one figure from the other one, and we will get the out of round. In this example it is 0.027 mm. And to get the taper figure, we need to subtract the lowest thrust side figure from the highest figure. In this case, the taper is 0.024 mm. Cylinders 1, 4, 5, 8 had out of round figures around 0.03 mm, and the taper also around 0.03 mm. The other cylinders had out of round figures around 0.05 mm and taper around 0.04 mm. Now is the question whether this is criminal wear or not. The manual doesn't say anything, only states the new condition figures. Although I found one BMW engine where these figures were stated, a diesel M47TU. It says that the max roundness and conicity allowed is 0.04 mm. I found some Mercedes Alusil engine data as well. It says max is 0.05 mm. Most of the Google and YouTube gurus say that 0.05 mm is still okay. The wear is there, you can slightly feel it with the finger, not the nail. So, with the full responsibility on my shoulders, I've decided not to machine the cylinder bores and leave them as they are. But what options you have in case you decide to fix the block? First one is to try to find a good block. These engines are rare, so you will most probably fail. The second option is to machine it and press in the cast iron liners. This is doable, but there is risk that the narrow bulkheads between cylinders will crack. This method is the most popular in Eastern Europe. And the third one is quite radical and rare. Try to rebore the B44 block to a bigger diameter and hone it using factory technology. Here is the proof that B46 is a typical B44 block, but only bored to a bigger diameter. The heads are different though. As this aluminum block contains stiff silica crystal, special stones should be used for boring. 3 steps of boring needs to be done with different stones to achieve the required surface grain and size. The 4th step is a special lapping process where the aluminum gets etched by a special silicone paste. After this procedure, the silica crystals are becoming exposed from aluminum, thus creating space in between them for the oil film. This technique is rare, but there are workshops who do this job, like this German workshop for instance. I will link their video in the description. Check it out how it's done. Here is what Kolbenschmidt brochure says about it. An additional long lifetime can be expected from an aluminum cylinder block reconditioned in this way. And here's the table with boring lapping sequence for the M72B46 motor, which is also made using Alusil technology. And here is the similar brochure from the Goodson, the honing equipment specialist in the USA. The stone sets used here are a bit different than in the Kolbenschmidt brochure. Since my cylinders have wear, I'm planning to give them a lapping round from the 4th step with this magical paste to slightly refresh their condition. I've managed to buy Sunnen felt set and the Sunnen AN-30 paste. It is really hard to get this paste, almost impossible. I've managed to buy 1 liter, a bit too much of course, but what to do. This was the only available size. Let's leave this for the next episode. Okay, let's check the piston ring gaps. The top ring gap is slightly above the spec. The middle one as well. The bottom also. So, the conclusion is that the rings reach the spec limit at around 200,000 kilometers. My engine has 230,000 kilometers. What options we have? 2 options. Do nothing or replace them. Some people say that if the compression is there and if the engine doesn't consume oil, leave those rings alone. I don't know what was the compression and the oil consumption, so I will replace them anyways, since I feel that this is the correct way, even though some people say that you cannot put new rings into an oval cone-shaped cylinder. Unfortunately, there are only original rings for sale. No any other cheaper alternatives exist, except 93mm piston rings made for Porsche Cayenne 4.5 liter turbo, but they have quite a big ring gaps. And according to the Hastings website, they are nitrile, and the BMW ones are more chrome coated. Not sure which ones are better, each material has its own pros and cons. That's a good option, I guess, if you are building a turbo or a compressor motor and need larger piston ring gaps. This Porsche engine is alusil as well. The 2 top rings fit well. The third bottom one doesn't fit, since the piston ring groove is a bit oval shaped. Few people were machining the third ring groove and it worked. New rings fit well after this procedure. Okay, let's measure the gaps of the new original rings. The gaps on all of the rings are smaller in comparison to old rings. They are still within the spec, but already at the upper limit, since I have worn cylinder bores. Also, some of the old rings were broken even without too much effort. I guess the metal is already tired. Anyways, I want to believe that this will improve something, so I've bought the whole set. Okay, let's check the ring axle play using a 0.05mm filler gauge. This should be in between 0.02 to 0.06mm. The groove wear is within the specs. I've read that piston skirts are coated with metal, so let's check this theory. Yep, indeed. Also, out of curiosity, I've measured the thickness of the old and new rings. Here is the data. Slight wear on all of the rings and a bit of more wear in the middle ring, which acts as oil compression ring. The middle ring, by the way, has a design called taper hook. which provides superior oil control and improved combustion gas management, according to Mahle piston ring brochure. This is the third oil removal ring. As you remember, the old ones were completely clogged with soot. In the next episode I'm gonna lap my ugly cylinder bores and commence engine assembly. That's it for today, and see you in the next one.